just want to get done with them. So the problem is as follows. You're given a two sets of numbers. So this is the problem. Given, so this problem one maybe, given two sets of numbers. So here the numbers are negative, positive, mixed. They're just integers. This and then there is minus 100, 50, 50, and 12. The exact numbers are not important, only that they are mixed. They are over integers and not just positives. So if you want to match the elements so that the sum of the product of the matched ones, of the pairs, maximizes. Okay, so maximize the sum of, I just say pairwise products. It's not precise word, but you understand what it means. Okay, so let us see. Unav, are you aware of this problem? Maybe you had missed that class. I don't remember. Then it's fine. Then it's okay. We'll discuss this. Also, if you have any doubts, I'll take it later. Let's see. So we have done this kind of problem for positive numbers, when the numbers are positive. Let us see how it works when they are negative, all negative. Oh, okay. Yeah, otherwise there is no matching possible. Right. So you can take anything. You can take minus 51 maybe. That doesn't matter. Or let's do one thing. Let me just make the number small for now, just so that you can try. So you can try with this particular one. Like, it doesn't really matter, because once you understand it, you can do. Yeah, just try with this maybe for now, because these numbers are too big to get any insight maybe. Okay. Mm-hmm. Okay, and hence -2 with -4. No, there is another. No, so there are more things. Okay. So you are saying that the same rule applies in this case also. Okay. -5. Yeah, sorry. But now, what is the explanation? You can explain for this case or in general also. Okay, so that's a good reason. Yeah, that if you multiply a big positive number with a negative number, I mean, if you, especially when you don't have to, then you get a bigger negative number. Right. So, well, in this particular case, let's see what the answer is. It's 15 plus 2 minus 1 plus 4. So actually, you see, it's interesting to note that, like this like is supposed to be like a smaller pair, but it is giving a bigger answer. Okay, 30 is coming out. So in this case, you can probably explain it, like you can probably prove it by checking the other cases. But try to think of a better reason or a more complete reason, maybe. Yeah, I think in this one you can put you have, as Ishana has said, I think it's a complete reason more or less, if I think. Like, because you can just say that if 3 is multiplied with 1, then what you get is less than 3 multiplied with 5. If 3 is multiplied with -1, then you get further less, and so on. So 3 multiplied with 5 is the best. Sorry? Closery number? Sorry, can you say that again? No, no. Here, so that's a different thing, right? So in that case, no, that's a very different thing. So this is, so if you remember the word we used, and it's actually a theorem, not just a word, it's the rearrangement inequality. Okay. So we are basically looking at rearrangement inequality, which we initially even explained a proof of. But let me just say, so in this case, we are taking two sets of numbers, and it's like if you multiply the bigger one with the bigger one, with the biggest one with the biggest one, second biggest with the second biggest, sorry, and so on, then you should get the biggest product. Is that right? Do you agree with me, Unav? Yeah, you should get the biggest product, especially when the numbers are positive. Then it's kind of like, yeah, that should be the answer. But the proof, well, we explained it in class. Let me not go into details of that. So that is what the rearrangement inequality was, right? That is very different from when the sum is constant and the product maximizes. When that is different. That's not very different, but that is a little different. But here we are actually doing the same thing, but now we have negative numbers. So it is not completely obvious that this will give the right answer. Do both of you agree? Unless you give a, yeah, right, unless you give a reason, it's not very obvious that this is the right thing to do. Though again, I agree, like, if there are negative numbers, then they should get multiplied, because together it's a kind of, and it's kind of, you can do some sub reasoning. But yeah, but now I want to do two things here. First thing, so basically this case, for the small case, it is very simple. But in general, we want to prove this. Okay, like let's say that there are 5 numbers on this side, 5 numbers on this side. So I have a plan here, which is like this: A1, A2, A3, A4, A5. And then there is B1, B2, B3, B4, B5. We want to think of and some of them may be negative, some of them may be positive. Okay, not writing that, it's clear. But in general, we have to argue in the end. How would you do a proof of this? That is the key. Okay. So how to prove that multiplying the biggest with the biggest and so on gives the right answer? Okay. So question is how to give a general proof. Okay. So there are several steps in this that one must try. So first of all, you must go over, means on your own, or you look, otherwise try, go over the proof in the of the positive case, right? So maybe let's do this one now again, because I have faith that if we do this thing, the positive case again closely, then you will really understand if it's needed for it to be positive numbers. Did we actually use whether the numbers were positive or not? Okay, so yeah, so let's do that. Okay. But you can also think of another type of proof by maybe saying, okay, maybe you can say that A3, let's say, for example, A3 onwards is negative, and let's say here you can say B4 onwards. You can probably just, for a general case, you can assume something like this. You should B4 onwards is negative, and then maybe you can give some kind of reasoning. Basically, I'm saying reduce it to the positive case. Okay, maybe you will say that negative numbers have to be multiplied with negative numbers. If there are more negative numbers in one of them, that should be multiplied with the least positive number. Those small things maybe you can use to construct a proof. Okay, please think about it. It's not, I don't think it's straightforward. Just think about it. This will work. But let's go over this proof for the positive case. So let me just pause here for a minute and see if you have any questions so far. We will go into the proof for the positive case, but so far, if you have any questions. No? Okay. So then let us come here. So we have A1, A2, A3, A4, A5, and let's assume that all of them are positive. So again, you guys may not be very used to this kind of thing because this is proofs, but this is how you'll have to get used to this, right? And obviously there is merit to this because we're proving things in general, which will apply for all numbers at the same time. This, and so what I want you guys to show is something very concrete. So I'm giving a simplifying it a little bit. So I want you to show that this, sorry, is bigger than so you can see what I've done here, right? I've taken some other matching, right? Some other permutation. One is matched with 2, 2 is with 3, 3 with 1, and 4 with 5, and so on. Try to show this. So I've not given numbers here, but the numbers are, I given a special case, okay, comparing it with one particular arbitrary matching. Okay, any ideas? Because again, we know that we are sure this is correct. Our intuition says this is correct, I should say. But how do you show it? Okay. Mhm. B2, B3 minus B2, sorry. Yeah. Okay. Okay, that is okay, right. But then what do you do with these things? This two, especially, I'm concerned about. Yes, and you can see why that's concerning also. Yeah, because we have kind of used A1, and if we have used B1 in one, like we have already used B1, but B1 is here. Yeah, so it's a little, right? Yeah. So maybe that's a little bit, I should say, complicated. So then let's put because if you remember the last time I had given a reason based on uh, swaps, kind of, right? Like this kind of situation, right? Where the things are exchanged, right? Like A4 goes to B5 and then, so A4 goes to B5 and B4 is matched with A5, right? So then this is easy. If this is the situation, this is easy, right? Because we can, and I pointed out that mistake I had made next time. But even if you don't remember, that's not the point. You can just see this here. See, this is obviously positive. You can just pair things and see, right? So let me write the final pairing, because here you will notice, and this by no means is proving the entire thing. We have to do the rest thing, but ask yourselves, both of you, are we using the fact that these numbers are positive? Like these are all same things, but are we using the fact that these numbers are positive for this particular thing, for this particular two pairs, A4, B4, A5, B5? I know. Positive. Positive. Yeah, this was right. No, right? We have not used positivity. This is, nevertheless, this is true. Okay, that's the point. From here, you can at least sense this, that we are not using positivity. And this carries over to all kinds of statements and proofs where we do this kind of thing, where we prove things step by step. Okay, and we do this kind of small shifts that increase the value. We are not using the positivity. That's not needed. That's why we'll come to the thing, but that's why this is called a combinatorial inequality. It's because most other inequalities, you will see that positivity is a very important condition. AMGM, harmonic mean, all those things, you will need positivity. But this particular one does not need. Okay. So yeah, let's come to the thing. So this part is clear. And now you can also sense another thing. Now, see, what we are doing is I took this part and compared this part. Okay. And I got this. Okay. You see, you will also understand, simply put, that this portion has nothing to do with the rest of the things. This has nothing to do with these two. There's this another group. Okay, both of you agree with this? What happens in the world of A4, B4, A5, B5 has nothing to do with this world. Right. Like, because one may say that, okay, you are grouping A4, B4, A5, B5. Are you not losing anything? Because you're losing, like, it's positive. What if it's greater than 2? And what if this one is -1? This difference is -1, then I will not be able to do it. But you see, that should not happen, because this world is different from that world, right? Because it's like the problem can be broken up. So this is the right way to break the problem. because of the nature of the matchings in this case. The nature in which we have matched things is like that. Now, all this is very obvious once one understands things called, like, every permutation can be broken up into cycles and things like that. Then it becomes very apparent that it's the right thing to do, but you can now see it. Okay. Okay. So now, so let us tackle the other group simply. Right? It's very simple. So I'll just remove this because this part is done, and we understand that it's a separate thing. Usually inequalities are not like that. If you group one part and you do forget the other part, then that part may be negative, this positive, and it cancels, but you have lost that while grouping and so on. But here it will not happen because that's an independent portion of the problem. Okay, so then how should we group this is the question. So let's isolate the thing and write it like this. I'm not doing anything, I'm just writing it. You guys have to think. We want to somehow group things and show that this is positive. So this is negative. So I also do not know how to do this without some formula, but I don't want to use the formula. By the way, there is a formula called Abel summation formula. If you are good at algebra, I don't know because I've not discussed much algebra. Abel summation formula, if you see that, you can easily, like that, this gives a one-line proof of this. But yeah, we are not doing that here. But this one, we should be able to give a reason ourselves. Or you can give some other reason also. That's up to you. You don't have to do it algebraically. Which common? Okay. 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 So you're grouping like this, right? And similarly, the last one, right? How do we show that this is positive? So let me just rewrite it a little bit. So you can see that the last two terms are negative. I mean, in a sense, you can understand. And the first one is positive. Somehow that first term, b1 times a1 minus a3, has to overwrite the other two terms. You can already kind of see it because you see the gap between a1 minus a3 is bigger than the gap between a1 minus a2 and a2 minus a3. Right? And also b1 is bigger than b2 and b1 is bigger than b3. So it seems correct, but how do we actually prove it? So this I'll leave for exercise. Okay, you can think of a reason. Please try this, both of you. You can think of some algebraic reason, or you can draw some picture and try. But you can try to show that this ends up being positive. So maybe the area of this. So you draw these three rectangles, these three, and try to put these two rectangles inside of this one somehow by some shifting, some reasoning, right? Cut paste, or just show it by some algebraic manipulation. This is not a trick that is used here. In many inequalities, to name a few, there is something called Chebyshev inequality, Schur's inequality, and many more which I don't know of. They use this kind of trick in more elaborate ways, but this is the beginning in some sense. Okay. So please finish this. Okay. So think of a reason. Try this. Okay. Okay. So yeah. So can anyone summarize what we have learned so far from here and about the negative case also? And like, how do we understand this problem about positives better? And do we understand it enough to say that we don't need positive? Right, exactly. Because all the reasoning we are doing is based on the comparison between the numbers, right? It is not about positive or negative. Okay, negative will actually make the situation better, right? I mean, if this b2 is negative, then it's actually good for you. Okay, so you can, so we are quite sure that you don't need negative, but have we proved the theorem? No, we have only taken some other matching, some other way to pair it. This is just some other way to pair, right? There are 120, 119, 118 more ways to pair it. 120 in total, two of them are already here. So we have to consider all of them and do, I don't know, there is some better way, but we are not going into that. Right, okay, we are not going into that. Okay. That can be done, but for that you need a better understanding of permutations and so on. So, or some algebraic formula like this from here, which also is easy to understand, but yet we don't have the language to understand summations that well. So I'm not doing it. Okay. So we have completed rearrangement inequality in general, in some sense, like we don't need positive or negative. So that's a good news. Basically, negative only makes it better. That's the thing. Okay. So far, so good. Let's now come to problem 2. Or maybe just 1 second. Sorry. Let me just give you another homework related to the last, which kind of uses a similar technique. Okay. So given this may be a little surprising because apparently there is even no order in this. In reals, show sorry, 1 second. You guys may have seen this kind of things while proving identities. This kind of expression appears all the time. Especially, I'm just talking about if you've done from a Bengal board, they have a lot of questions like this. But you've seen it or not, doesn't matter. Let's try this. I mean, let's try this for homework. So we want to show that this is positive. So you don't see many squares, and we don't have any order also. And also the numbers are not given to be positive. But still this holds. Okay. For, yeah, just think about this. You can note it down.
So there's no relation between these two things.
Yeah, there is no relation. Apparently there is no relation. But yeah, you have to try. So you can take special cases. Maybe you can take a relation and try, and then and maybe then take another relation and try, or just see. The ideas are very similar. So problem 2. If sorry, 1 minute. So the numbers are between 0 and -1, -1 and 0, and we wanted to rather show that yeah. So let's think about this. And you guys know that you have to try to use induction. That was the context in which I discussed this and so on. So any ideas? See, we are supposed to use induction. We are supposed to like prove it from the case of one, when there is only one, when n is equal to one. From there, maybe build it to two, build to three using induction. Yeah. I mean, so the base case is obviously true. I mean, this is obviously, I should put greater than equal to. This is obviously true. There's nothing to. Now you have to kind of assume that it is true for some k and then try to prove for the next case somehow. You know how to do that mostly. But only that there are negative numbers, so we are a little have to be careful whether we can multiply both sides and such things. Certainly, right. This one is certainly always positive, no doubt, because 1 plus ai is positive. So let's run the usual induction route, right? Let's go and see. So we shall say you assume that it is true for some k. Assume 1 plus a1 all the way to 1 plus ak could even be 2, is that this holds. Now, how would you use this to show for k plus 1? This is in some sense exactly the same as what we had done, but just in the reasoning, maybe we'll have to see a little bit more. But the steps would be the same. So now there are k plus 1 things, and we want to say this. Okay. Mm-hmm. Uh, what was the last? Oh, this is AK plus 1. Okay, yeah, we can call it D. We'll just call it small d because it's okay. C plus D, right? So what's the natural thing to do? So the natural thing is to just multiply this inequality that we know, multiply it on both sides by 1 plus D, right? So if you multiply both sides by 1 plus D, then what do we get? We get C times 1 plus D. But is this true? Can you multiply both sides? Because yeah, right. Is this legal? So remember 1 plus D is positive, so that's not a problem. But can there be any other problem? Oh, so I've just multiplied both sides by 1 plus D. Right, yeah. And now my question is that correct to do? Like, is that legal to do? That's certainly what we want to do. There's no doubt, right? Because you want to multiply, you want to have 1 plus D factor on the left hand side extra. So we multiply, so we have to multiply both sides. So is that legal to do? We remember 1 plus D is positive, B is positive, but C may not be positive, right? So C may not be positive. C can be positive or it can be negative. It could be anything. It could be both. I mean, it could be anything. But is that a problem? So a situation is like if 5 is bigger than 2, then you can certainly multiply both sides by 4, right? There's no problem with that. But if I say 5 is bigger than minus 2, then can you multiply both sides by 4? Yes, right? Like, yeah, because if C is negative, then this will be negative, right? So let's write that. If C is negative, then C plus 1 by D is negative. And sorry, is negative. But then if it's negative, then there's obviously no problem, right? Because then it's like this, and because left hand side is positive. But you have to say this. You can't just say, I mean, you can say, but you have to know, and if needed, you have to say. It depends on the situation. You should know this. That because the lesser side is negative, that's why you're able to do this, right? Otherwise, you cannot do it. Yeah, you can take examples and see. So this is a very easy thing, but you have to just notice it. Okay. But now what do we do? So, I mean, I'll just write it in the older notation also, because maybe that can also just so this is what we have in both the notations. So what do we have to do now, right? So now we need to show that the right hand side is bigger than what we need, right? We need to show that this thing is bigger than 1 plus. You guys agree? Because this will finally complete the result, right? Or basically, like, we have this, and now we want to show in that notation that it is till ak plus 1. Because that's what we finally want to get to. And this is the same thing we have done several times, similar thing, that you multiply both sides and you get to this thing, and now you want to show that this lesser one is bigger than what we want to show. So then the bigger one is obviously bigger. Where? Mm-hmm. Okay, so this is what we want to show. Okay, so let's write that. It is the same thing as what we want to show. B minus D is bigger than C minus BD. Okay. Oh, yes, yes, yeah. That's you're saying is the better things. Okay. Right. We know that. Yes. No, 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 no. Why is 1 minus B negative? D, no, no, no. D is not necessarily positive, right? D is just AK plus 1. So the D here, the notation in which you're going, is just AK plus 1. That's what it is, right? And even if you assume it is positive, you see 1 minus B is actually positive. Actually, B is less than 1. Because you see, this condition is giving that 1 plus AI is actually less than 1. You see, it's actually the complete, yeah, complete opposite in some sense. But that's actually not a bad thing, right? Because, so, I mean, no, 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 sorry, nothing. So both things are positive or maybe, yeah. But yeah, if, so from here, actually, we do get something, right? So we know that 1 minus B is always positive. So 1 minus B is always positive. Now, if D is negative, then we are done. Right? Okay. So actually, this is what we gain from this, manipulation. That if D is negative, then there is nothing to say because then it's negative. The whole thing D times 1 minus B is actually negative because 1 minus B is positive. That's always positive. Okay. No, b is actually less than 1. Like, it looks like b is 1 plus a1 times, but it's actually, each of the factors are actually less than 1. So if d is negative, then there is nothing to do. That's a good news for us. Okay. So now we need to only focus on the positive part. Okay. And now we can try to see what to do. So assume d is positive. So that last, but you have to use this somehow, right? You have to use this thing. Otherwise, you cannot finish the problem.
Yes.
Right. So how do we use it? So basically, you have to come down to this. The d is positive. This is positive. Remember, this is positive. Yeah, that looks a little strange, right? Because this thing may actually be negative. This thing.
Mm,
Okay. So if c is positive, then we are done again, right? So this is another case. So basically, we can look at the last case, which maybe looks wrong for a second, but let's see. So if c is positive, then we are done because, so why? Can anybody give a reason?
it's like saying
C into 1 plus d is greater than c plus d. Yeah. Um, no, but then that's not obvious, right? Yeah, that's not obvious. Yeah, that is also not obvious. So we have to really do this to see. Yeah, I was not expecting it to go like this. I thought it would be simple. So let me also think. Hmm, maybe I'm missing something very simple. So let us just expand it. So I'm just expanding it. So I'm just expanding the left-hand side. We can use the case for 2, but it will not be exactly be left, will be left with more casework. Okay. See, if you just expand things, then we can do some cancellations. So let's just bring this up. Oh, 1 minute. Yeah, right. So if we expand this and simplify, we will be left with showing that this is positive. Right? If we just cancel things. But this is definitely not necessarily true. Right? This is not necessarily true because this thing, this summation could be, because we know that AK plus 1, which is D, we know that this is positive, right? But this may be negative, right? So if A1 to AK, this whole summation, if this is negative, yeah, then we are in trouble. Damn, we are just missing something. I think. So you guys see the problem, right? Yeah. Is it? Do you see the problem? Hello. Yes, right. Because if that thing is negative, if A1 to AK is negative, then there's a problem. No, but when I the question, there was some simple reason, I think. But let's just think. So what will happen, I think, now is that this case in which A1 to AK is negative will actually have a simpler reason. So if A1 to AK is negative, if it is, yeah, I mean, basically, if it is less than -1, then there is a real problem. But that is, I'm just thinking to myself. -1, there is a problem. If it is less than -1, then it is. Yes, right. So see, if uh, if A1 to this thing, okay, if this thing is bigger than -1, right, then you can actually just call this A, and then what you need to prove, like this flipping box, this actually becomes this, which is basically the same problem for the case of two variables. Okay, this is just the same problem for the case of two. This is just a problem for the case of two variables. So we need not worry about this. This we have already, we are done with this. So is this part okay? Like, so we just forget about the expansion for a second. That will just create more confusion. So forget about the expansion. So basically, when you see this thing that you need to prove, this last pink thing, this thing, then you should immediately see it like the same problem, but for a smaller case. This also was an idea we had seen last time. So this is like the A, capital A, right? And this is capital A. Then you can see it is the same problem for the case of two variables. But for that, we need the fact that A is bigger than -1. So that's why I've written it, okay? See, the other case is very simple. If A1 to AK is less than -1. Well, if it's less than, because that's the other natural case to consider, right? Because that's the case in which the problem is not kind of induction kind of doesn't work, right? So you see, but in that case, what we get is that, in fact, this is negative.
Yeah.
Yeah. So if that is, so 1 plus this is negative, okay. Yeah, so then how do you do the problem in this case? So then the C, basically the C is negative. Okay, that is the C is negative. And this we had, yeah, maybe this follows from something. So right. But then 1 plus, yeah, right. But if C is negative, then, or if this is negative, what do you need to prove finally, right? Finally, I'm just changing it here, okay? We make this K plus 1. See, this is what we want to prove for K plus 1. Okay, but then this will also be negative, right? Because, I mean, AK plus 1 is negative. One plus this thing is obviously also negative. Okay, but then there is nothing to prove, right? Then if you look at what you have to prove, then that's just a trivial statement. This is just a trivial statement because the left hand side is positive and the right hand side is nil. Like then there is nothing to prove even. Okay, let me just re-say the whole thing again because I just made a little bit of mess, but that's the whole point. This is problem solving. Solutions are not known. We have to figure it out. But let me just run through it again. Okay, you guys should also do that, or maybe I don't have a generalization of this right now, so I'm not giving, but let us see. Basically, the thing is that if we want to, I will not do the proof, I'm just going to say the summary. We want to show this, okay? So if is negative, then nothing to do. If you get that at any point that something is like this is negative, then there is nothing to do. If this thing is positive, apply induction. Okay, but basically what happened, we were trying to apply induction, and when we did the inductive step, there we saw that, you know, when can you apply induction in the case for two variables? That was the case in which this is positive. Then we said, okay, what do we do when it's negative? But then we looked at the problem for that, and that's obviously the problem is trivial in that case. Okay, just try to write the proof again. Okay, try to go over it again and see. Okay, all right. Let me just also check if there is a similar problem I know, or I can check it out because I had basically taken this from, means it's a standard problem, but I had taken it from Wikipedia. Okay, but it's standard. You'll find it in any inequality handout or book or anything. But I just want to see something. We won't discuss more problems today. I think it's already we discussed. So let's see. I'm not giving you a reference to read because Wikipedia is very difficult to read, maybe for now for you guys, but soon you will be able to. You will. Oh God, I don't even find it here. Then how did I give this? Ah, okay, yeah. Yeah, I kind of had added a little bit twist. That's why I got confused myself earlier. Okay. So in the same thing, you will see that there is another problem where the exponent is negative, and I have asked. Okay, so just go have a look at it. You would have in your notebook and just try it. Okay, just try that, and then that's it for today. Okay, when was the other day, Ishana? You said you will be available.